I mentioned the idea of time value of money during one of the synchronous meetings. Someone asked me how much math we're going to see on the final exam, and my answer was not too much. But I do really want to talk about this bit of math. It's fairly simple. It's basically just algebra, but it's incredibly useful. So let me show it to you in a spreadsheet where we can have the computer do all the hard work. So here's the question to start with. Very often you'll see lotteries. You'll see lotteries advertised that say something like, we will give you $1 million a year for the rest of your life. More often it's something more like, we'll give you $1 million a year for the next 30 years. Now, and it's actually going to turn out to be an even easier question to solve of how much would something be worth if it's $1 million a year forever. So we're going to think about, well, let's think about each of these three. So 1 million per year for 30 years. Ooh, where'd it go? For life and forever. So it's tempting to think that for 30 years, this is going to be worth $30 million. And this is a bit of bad advertising that lotteries engage in, is they will tell you this is a $30 million prize, but you read the fine print and it's actually, well, $30 million over 30 years. That is not worth the same as $30 million right now. So we're going to think about how much money would you need to put away if you were running the lottery in order to give out this prize. That's going to tell us what is the actual value of this, and that's going to help us to figure out these other two possibilities. So we'll say at some time period, we'll start with time period 0. We'll look at some payment. I'll just say, ooh, that's not what I want. I'll just say 1 for now, 1 million. And then this will be this plus 1. And let's go ahead, going from 8 to 28. Oh, that's not what I want. Control C, copy this down to here, paste, there we go. No, is that right? I can't do math. All right, this is why we get the computer to do it. And we're going to have a $1 million payment the whole way through. Control C. Ooh. Let's try this one more time. There we go. Paste. There we go. So we're getting $1 million every year. And we can say, how much do we get total? The sum of all of these payments to, I think this was B8. And we got 30 million payments. B8. Cool. So we're calling it a $30 million lottery. How much do we need now is the real question. So time period 0, that's you turn in your lottery ticket, you say, I won the $30 million prize. They say, great, here's your first $1 million. They need $1 million on hand to get that. Now, how much do they need to get $1 million, let's say 30 years from now? Well, if they put money away now, they'll get some interest growth, and so they'll need to put away a lot less than $30 million. It's a lot easier to figure out what they need to get 1 year from now. We just have to ask, what sort of interest rate can they get? So let's just choose a nice round number. We'll let our interest rate be 5%, right? 5% of 1, 0.05. And so if we put away $1 million now, we're going to end up with $1,050,000 in a year. So we're going to need something between $1 million and $50,000 less than $1 million. What's that? 950,000. So it's going to be something bigger than 0.95. So essentially, what do we need? Well, let's switch really quickly to the whiteboard and think about the math here. It's actually going to be a little bit easier for me to think about this in mathematical terms. So the future value of some investment, I know this has a little bit of glare, but this says FV for future value equals the present value times 1 plus the interest rate to the power of the compounding period. How many times do we repeat this? So if you put $1 million into the bank and you get 5% interest after a year, you have $1,050,000. After 2 years, you're going to have that plus 5% of $1,050,000. 3 years, you're basically increasing the size of T. So we're saying $1 million times 1 plus 0.5, which is really just 1.05 to the power of T. This is our future value. What we really want to know is what is the present value. And so in this case, instead of a present value of 1, we want to know how much do we need now to get $1 million in a year. So our future value is going to be 1. Let me try with blue. Maybe this will be a little bit easier to see. So now, let's divide both sides by this stuff, 1.05 to the power of T. In this case, T is 1 for what we're looking at right now, 1.05 to the T, and we've got present value equals 1 divided by 1.05, right? For T equals 1. When we're asking what do we need 2 years out, we're just going to make this to the power of 2, right? Let's go back to the screen. So what we need is 1 over 1 plus the interest rate. So 1 divided by 1 plus this, which, let's see if I can remember how to do this. Well, yeah, whatever. $E$4 is going to make my life a little bit easier there. If you're working in any sort of a spreadsheet, Excel, Google Sheets, or in my case, LibreOffice, that little $ operator makes it, it just makes life easier, right? Let me show you that really quick, because that's a helpful thing. We can refer to a cell, and then we can copy stuff, and what you'll see is now we're referring to the cell beneath it. We copied this down to here, and it moved the reference down, which is really helpful behavior. Let's change this to $E$3. When we copy it now, it's always going to the same thing. Let's go back, equals E3. And then if we copy this, there we go. Now we're getting F5 because we moved 1 column over. And here, we did this earlier, but it moved 1 row down. So that's why I put in those $signs. Let me clean this up. We'll come back to this. And let me also add, all right, I haven't done it quite right yet, have I? Oh, there's the problem. I said 1 over 1 plus 0. And what I actually want is E3. So $0.952 million will grow to be $1 million after 1 year. Let's make this actually even a little bit better. That's not right. To the power of the number of years going forward. So what this formula is telling us is we need 1, right? So we're thinking just $1 million. If we were to change this, we would change that to something else. And actually, you know what? Let's go ahead and even change that now. We'll call this B9, right? So that's referring to 1 divided by 1 plus the interest rate to the power of the number of years we're waiting. Right? So now we should be able to copy this down. And 2 years out, we can see we need 900,000. 3 years out, we need even less. And as we keep going, we need less and less and less. Let's go all the way out to the 30th year, or the 30th payment, 29 years out. And we only need $250,000 to be able to make the whole thing, right? Or to make that very last payment. So if you and I are running the lottery, we're telling people, here's this $30 million prize, but we only need to get $16 million now in order to give out this prize. So if we were to sell $20 million worth of tickets, we could advertise a $30 million prize, even though we didn't bring in $30 million. If we can safely expect to get 5% interest, then over the next 30 years, we grow that 16 million initial dollars. Really, it's $15 million because we immediately give away the first million. But we put that money into the bank, we let it grow, and that means that by the time it's time to make that last payment, that $250,000 has grown to a full $1 million. This is a double bummer for the person who won the lottery because they're also going to be losing some inflation to this. That $1 million isn't going to buy them $1 million worth of stuff if there's been inflation. So here's the big idea. When we're thinking about the value of this $1 million per year over 30 years, it's not worth $30 million, it's worth $16 million, because that's how much we need to put away to be able to make good on this ticket, on this lottery prize. Now, if we're asking about how much is it worth if it goes for the rest of your life, well, then we have to ask the question of how long do you live? That brings us into a field called actuarial sciences, which is basically, well, this is what insurance people are doing. This is what the insurance company, they hire actuaries to try and estimate the risk of any particular thing. So if you buy life insurance, they're not going to say, we'll give you $1 billion in life insurance for $5 a month, because they know that at some point I'm going to die and my heirs are going to get $1 billion. They couldn't afford to do that because they wouldn't have enough money raised by the time I do die. If I was 80 years old and looking to buy $1 million life insurance policy, I'd have to pay pretty close to $1 million up front. If you're 20 looking to buy $1 million health policy, you probably are going to live a long time. So if they charge you a small amount over a long period of time, they'll eventually raise enough money to cover their obligations when it's time to make a claim on that insurance policy. So for the value of $1 million a year for life, it's going to depend on the age of whoever wins and their health and all the things that are going to affect how soon they are, how soon the lottery company has to stop paying out. So if we expect to live for 30 years, well, then the policy is going to be worth $16 million. If we expect to live more than 30 years, it's going to be worth more than that. Although, here's a cool thing for the lottery company, which is the state, not really a company, but for the lottery commission, if we're expecting people to live, say, 31 years, well, adding that last year only adds $230,000 cost, right? If we've got someone living a much longer time, 45 years out, they only need to put away $100,000 to cover the possibility of someone living to 45 years. So the further out we go, since there's that much more time for compound interest to work, we need relatively less to account for this. So let's just take a quick look while we're here about how big this is. Oh, that's not what I want. There we go. $18 million. So we've taken a 30-year prize and we've made it actually a 46-year prize. So we've added 50% to how many payments we're making, and we've added $2.5 million to the amount of money the lottery commission needs to put away, right? So we're adding years far out in the future. Those years are not worth very much. And that is going to help us to make sense of the next part of our question, which is how much is this worth if we get $1 million a year forever? And the answer is, it's going to turn out to be not very much. Now, one way we could do this is we could just keep adding rows to our spreadsheet, and eventually we're going to run out of rows, but let's take a look. How many rows have we got? That's 1 million rows, right? So how much is $1 million a year for 1 million years compared to $1 million a year forever? Well, it's going to be basically the same, right? $1 million. Actually, we can take one of these rows. Put that here. And let's make this 1 million. And we get a result that's so small, we can't even figure it out. Let's make this 1,000. 1,000 years out, we run out of decimal places. We need to add even more decimals, right? So the amount, this is the time traveler's dream, right? You go back in time, you put a penny into your bank account, and then you come back to the present and you're a billionaire. And this is exactly that logic, right? So once we're 1,000 years out, that extra $1 million 1,000 years from now, because it's so far into the future, it's worth very, very little in present value terms. So what that means, well, two things it means. One is that we don't actually need to drop this down to 1 million rows and add up the results for 1 million rows. We could, but it looks like by the time we're at 1,000 years out, we're looking at fractions of pennies, right? So you just throw an extra dollar on top and you're way ahead. So the answer, well, one way to get the answer is just that brute force approach, but there's actually a much easier way to get the answer. The way we get the answer is we ask, how much money do we need so that the interest payments are equal to $1 million? And if we have an interest payment of $1 million, we take it away, we're left with enough so that next year the interest growth gives us another $1 million. The question is actually a lot easier to answer here, right? The value for 30 years, we've got to do 30 calculations. The value for forever is just, we need to figure out how much money do we need to put away so that at 5% interest, each year we get $1 million. And the answer here is going to actually be just $20 million. So for this, it's actually going to be 1 divided by our interest rate, $20 million. That's the math of it. I'm not going to do the math because I'm going to confuse myself, but this is called a geometric series, and a really useful place to see this is if you go to the YouTube channel. My favorite explanation of this idea, I think the URL still works, Jim Bob Jenkins. This guy, he was an RIT student who started this YouTube channel 1 million years ago, and now he runs Game Theory 101.com, and I think actually now the YouTube channel is called Game Theory 101. Actually, you know what? As long as I'm sharing my screen, let's go ahead and take a look. Game Theory 101.com. Ooh. Game Theory 101.com. There we go. And if you look at the courses, or actually even better, you look at this. In game theory, the way this comes up is when we're thinking about how do we cooperate. Subgame, centipede, strategic form, infinite strategy space, expected utility theorem. This is useful stuff. It's in here somewhere, but you guys don't need to watch me do this. Series, geometric series, and infinite payoffs. There we go. So let's pull back to the original question, which is, how do we think about the value of something in the future? So something like you get $1 million forever, it's tempting to say, well, therefore it's worth infinite dollars. But that's not really the case, right? So one case where this is really important is, what is the value of, say, a share in Apple Corporation. You buy a share of Apple because you expect one of two things to happen. Either you expect the share price to rise, or you expect that you're going to get paid dividends and you're willing to pay up front now so that you get a lot of dividends in the long run. Fundamentally, the value of a company's share has to do with this expectation of what do we expect to get paid in terms of profits, dividends, and the value of the company in the future. Right? You're asking a question about how much do we get in the future. Now, something like Apple, it's a corporation. It could fundamentally last forever. There's nothing preventing it. It's not a mortal being. So we can ask, how likely is it that it does last forever? Well, not terribly likely that it'll last forever, but it might last for a long enough time that it's as good as forever when we boil down the math. So given that, we ask, how much should I be willing to pay for one share of Apple? Well, I have to ask, how much do I expect to get in terms of dividends? So maybe I expect something like this, where I get, say, $1 worth of dividends every year forever. Right? Now, just to be lazy and not have to update the numbers. If I'm expecting some amount of money every year, I can use this time value of money math to discount money in the future, accounting for the fact that money in the future is just not worth as much as money now. I can't spend it now. I've got to wait for it. I also have to think about what's my opportunity cost, what's my next best alternative. If I expect to get $1 3 years from now, well, if I put away 86 cents in my bank right now, I'd get that dollar anyways, right? So I shouldn't be willing to pay more than 86 cents if this expectation is valid, right? That's going to put an upper limit on how much people are going to be willing to pay for Apple shares. Right? We're getting infinite dollars if we hold on to this stock forever, but we're not willing to pay infinite dollars because we have some idea of how much do we actually need to put away. So that's time value of money in a nutshell. Right? The basic idea is we take a whole series of payments and we compress it down to a single number and ask, is it worth it, yes or no? Now, the really cool thing is thinking about the Apple example. We have a market for Apple shares. We have people buying and selling those shares. So the price is determined by the interaction of supply and demand. And the outcome is we have some price that is basically a collective estimate, right? It's a crowdsourced estimate of how valuable is this company given everything we know about the situation they're in and our opportunity costs. We're aggregating a ton of information and boiling it down into a simple figure that's easy to understand. Share of Apple is $300 or whatever it is today. It's some amount, and that some amount basically means we're looking at something like this $16 million. It means we think that the total value, right, the market cap is, let's say, $1 trillion. The market cap of Apple is $1 trillion. That's everyone in the market estimating that based on some conceivable alternative interest rate that we might get, some way that we might grow our money besides buying shares of Apple, given what we expect Apple to do in the future, given what we expect to happen in terms of changing competitive landscapes, we've got this big estimate with lots and lots of people thinking about it. The figure that you see on the stock market is basically as good an estimate as we're ever going to get. Now, that said, the goal of any investor is to try and make a better guess. So let's say you go out and you do some research and you find out, hey, they're introducing a new product. It's a new thing, whole new market. It's like the iPhone, except even more so, and it's going to change everything. And if you know this before the rest of the market does, you can buy Apple shares at the current price where people have current expectations, and then when things change, your shares are going to be worth a lot more money. Right? This is fundamentally what the stock market is people trying to make forecasts about what they expect to happen in the future for any given company. In the case of something like Apple, we got a lot of people making a lot of estimates. We got a lot of really talented people hired by the big investment banks. So someone like you or me, we don't really have much of a chance of outguessing them. It's basically a bad idea for you or I to try and pick stocks. But fundamentally, the market is a lot of people trying to pick stocks, and the price number we get boils down to this thing we started with, some estimate of the value, the discounted future value of all of the dividends you expect to get from Apple, given everything we know about the market they're operating in, who's managing them, how things are likely to turn out, how consumers are likely to respond, given all these various things that are going to affect the overall productivity of this company. The price that we're seeing on the stock market is giving us this collective estimate that accounts for all of this stuff, which is really cool. Let's close it there. I don't want to go too far afield, but let me just close really quickly. The time value of money is some relatively simple math, right? You can look this up. Investopedia is going to have a pretty good article. We are fundamentally doing this. We're asking to get this amount of money in the future, this far into the future, at this interest rate, how much do we need to put away now? And the answer is less than this much, right? If we're going to get $1 million 1 year from now, we don't need to put away a full $1 million now because we expect that money to grow. We've got relatively simple math to account for that. And so we can use this math to ask questions like, how much is this $30 million lottery prize actually worth? Or if we expect Apple to generate $1 billion profit every year for forever, how much should we value the company as a whole? Cool. Close it there.